Well, first I should say thank you to Pier Giorgio Odifreddi and all the other people who were inviting me here. It's been a great meeting. I've enjoyed every minute of it, and I'm deeply grateful for being part of it. I wanted to begin just by a comment to the remarks of Professor Aumann, particularly, and about punishment. That was in the last session, which seems to me something very deep in human nature. I have some evidence to support this point of view, that punishment is in fact deeply embedded in our genes. In England, when I was a child, we had two big festivals. There was the Festival of Love, which was Christmas Day, 25 December. There was the Festival of Punishment, which was called Guy Fawkes Day, celebrating the punishment of this traitor Guy Fawkes, who had tried to blow up the Houses of Parliament in the year 1605, more than 400 years ago. And so we had these two festivals, the Festival of Love and the Festival of Punishment. And as children, we enjoyed the Festival of Punishment much more. Well, now I come to my text. I apologize for reading from a text so that I get finished in the appointed time. So I'm speaking now about mathematics, birds and frogs. And I read out the headings of there are 6 sections in the talk. And so the first section is called Galilei and Descartes. Some mathematicians are birds, others are frogs. Birds fly high in the air and survey broad vistas of mathematics out to the far horizon. They delight in concepts that unify our thinking and bring together diverse problems from different parts of the landscape. Frogs live in the mud below and see only the flowers that grow nearby. They delight in the details of particular objects, and they solve problems one at a time. I happen to be a frog, but many of my best friends are birds. The main theme of my talk tonight is this: mathematics needs both birds and frogs. Mathematics is rich and beautiful because birds give it broad visions, and frogs give it intricate details. Mathematics is both great art and important science because it combines generality of concepts with depth of structures. It is stupid to claim that birds are better than frogs because they see farther, or to say that frogs are better than birds because they see deeper. The world of mathematics is both deep and broad, and we need birds and frogs working together to explore it. At the beginning of the 17th century, 2 great philosophers, Galileo Galilei in Italy and René Descartes in France, proclaimed the birth of modern science. Descartes was a bird and Galileo was a frog. Each of them described his vision of the future. Their visions were very different. Galileo said, "Nature's great book is written in mathematical symbols." Descartes said, "I think, therefore I am." According to Galileo, scientists should observe and measure accurately what they see until the accumulated measurements reveal how nature works. Scientists will then induce from the facts the laws which nature obeys. According to Descartes, scientists should stay at home and deduce the laws of nature by pure thinking. In order to deduce the laws correctly, scientists will need only the rules of logic and knowledge of the existence of God. For 400 years, since Galileo and Descartes led the way, science has raced ahead by following both paths simultaneously. Neither Galilean science, Galilean empiricism, nor Cartesian dogmatism has the power to elucidate nature's secrets by itself, but both together have been amazingly successful. For 400 years, English scientists have tended to be Galilean and French scientists Cartesian. Faraday and Darwin and Rutherford were Galileans. Pascal and Laplace and Poincaré were Cartesians. Science was greatly enriched by the cross-fertilization of those two contrasting national cultures. Both cultures were always at work in both countries. Newton was at heart a Cartesian, using pure thought as Descartes intended, and using it to demolish the Cartesian dogma of vortices. Marie Curie was at heart a Galilean, boiling tons of crude uranium ore to demolish the dogma of the indestructibility of atoms. In the history of 20th century mathematics, there were two decisive events, one belonging to the Galilean tradition and the other to the Cartesian tradition. The first was the International Congress of Mathematicians in Paris in the year 1900, at which Hilbert gave the keynote address, charting the course of mathematics for the coming century by propounding his famous list of 23 outstanding unsolved problems. Hilbert himself was a bird, flying over the whole territory of mathematics, but he addressed his problems to the frogs who would solve them one at a time. The second decisive event was the formation of the Bourbaki group of mathematicians in France in the 1930s, dedicated to publishing a series of textbooks which would establish a unifying framework for all of mathematics. The Hilbert problems were enormously successful in guiding mathematical research into fruitful directions. Some of them were solved and some remain unsolved, but almost all of them stimulated the growth of new ideas and new fields of mathematics. The Bourbaki project was equally influential. It changed the style of mathematics for the next 50 years, imposing a logical coherence that did not exist before, and moving the emphasis from concrete examples to abstract generalities. In the Bourbaki scheme of things, mathematics is the abstract structure included in the Bourbaki textbooks. What is not in the textbooks is not mathematics. Concrete examples, since they do not appear in the textbooks, are not mathematics. The Bourbaki program was the extreme expression of the Cartesian style of mathematics. It narrowed the scope of mathematics by excluding the beautiful flowers which Galilean travelers might collect by the wayside. Section 2, Jokes of Nature. For me, as a Galilean, the main thing missing in the Bourbaki program is the element of surprise. When I look at the history of mathematics, I see a succession of illogical jumps, improbable coincidences, jokes of nature. One of the most profound jokes of nature is the square root of -1 that the physicist Erwin Schrödinger put into his wave equation when he invented wave mechanics in 1926. The Schrödinger equation describes correctly everything we know about the behavior of atoms. It is the basis of all of chemistry and most of physics. And that square root of -1 means that nature works with complex numbers and not with real numbers. This discovery came as a complete surprise to Schrödinger as well as to everybody else. According to Schrödinger, he had a 14-year-old girlfriend, Ita Junge, who said to him at the time, "Hey, you never even thought when you began that so much sensible stuff would come out of it." All through the 19th century, mathematicians from Abel to Riemann and Weierstrass had been creating a magnificent theory of functions of complex variables. They had discovered that the theory of functions became far deeper and more powerful when it was extended from real to complex numbers. But they always thought of complex numbers as an artificial construction invented by human mathematicians as a useful and elegant abstraction from real life. It never entered their heads that this artificial number system that they had invented was, in fact, the ground on which atoms move. They never imagined that nature had got there first. Another joke of nature is the precise linearity of quantum mechanics. the fact that the possible states of any physical object form a linear space. Before quantum mechanics was invented, classical physics was always nonlinear, and linear models were only approximately valid. After quantum mechanics, nature itself suddenly became linear. This had profound consequences for mathematics. During the 19th century, Sophus Lie developed his elaborate theory of continuous groups, intended to clarify the behavior of classical dynamical systems. Lie groups were then of little interest, either to mathematicians or to physicists. The nonlinear theory was too complicated for the mathematicians and too obscure for the physicists. So Lie died a sad and disappointed man. And then, 50 years later, it turned out that nature was, in fact, precisely linear, and the theory of linear representations of Lie algebras was the natural language of particle physics. Lie groups and Lie algebras were reborn as one of the central themes of 20th century mathematics. A third joke of nature is the existence of quasi-crystals. In the 19th century, the study of crystals led to a complete enumeration of possible discrete symmetry groups in Euclidean space. Theorems were proved, establishing the fact that in three-dimensional space, discrete symmetry groups could contain only rotations of order 3, 4, or 6. And then in 1984, quasi-crystals were discovered, real solid objects growing out of liquid metal alloys, showing the symmetry of the icosahedral group, which includes five-fold rotations. Meanwhile, the mathematician Roger Penrose discovered the Penrose tilings of the plane. These are arrangements of parallelograms which cover a plane with pentagonal long-range order. The alloys are three-dimensional analogues of the two-dimensional Penrose tilings. After these discoveries, mathematicians had to enlarge the theory of crystallographic groups so as to include quasi-crystals. This is a major program of research which is still in progress. And my fourth joke of nature is a similarity in behavior between quasi-crystals on the one hand and the zeros of the Riemann zeta function on the other. The zeros of the zeta function are exciting to mathematicians because they are found to lie on a straight line and nobody understands why. The statement that with trivial exceptions they all lie on a straight line is the famous Riemann hypothesis. To prove the Riemann hypothesis has been the dream of young mathematicians for more than 100 years. I am now making the outrageous suggestion that we might use quasi-crystals to prove the Riemann hypothesis. Those of you who are mathematicians may consider the suggestion frivolous. Those who are not mathematicians may consider it uninteresting. Nevertheless, I'm putting it forward for your serious consideration. When the physicist Leo Szilard was young, he became dissatisfied with the 10 Commandments of Moses, and he wrote a new set of 10 Commandments to replace them. Szilard's second commandment says, "Let your acts be directed toward a worthy goal, but do not ask if they can reach it. They are to be models and examples, not means to an end." Szilard practiced what he preached. He was the first physicist to imagine nuclear weapons and the first to campaign actively against their use. His second commandment certainly applies here. The proof of the Riemann hypothesis is a worthy goal, and it's not for us to ask whether we can reach it. I give you some hints describing how it might be achieved. Here I will be giving voice to the mathematician that I was 50 years ago before I became a physicist. I talk first about the Riemann hypothesis and then about quasi-crystals. There were until recently two supreme unsolved problems in the world of pure mathematics: the proof of Fermat's last theorem and the proof of the Riemann hypothesis. 12 years ago, my Princeton colleague Andrew Wiles, who was here last year, polished off Fermat's last theorem, and now only the Riemann hypothesis remains. Wiles' proof of the Fermat theorem was not just a technical stunt. It required the discovery and exploring of a new field of mathematical ideas, far wider and more consequential than the Fermat theorem itself. It's likely that any proof of the Riemann hypothesis will likewise lead to a deeper understanding of many other diverse areas of mathematics, and perhaps of physics too. Riemann's zeta function and other zeta functions similar to it appear ubiquitously in number theory, in the theory of dynamical systems, in geometry, in function theory, and in physics. The zeta function stands at a junction where paths lead in many directions. A proof of the hypothesis will illuminate all the connections. Like every serious student of pure mathematics, when I was young, I had dreams of proving the Riemann hypothesis. I had some vague ideas that I thought might lead to a proof. In recent years, after the discovery of quasicrystals, my ideas became a little less vague. So I offer them here for the consideration of any young mathematician who has ambitions to win a Fields Medal, the mathematical equivalent of a Nobel Prize. Quasicrystals can exist in spaces of 1, 2, or 3 dimensions. From the point of view of physics, the 3-dimensional quasicrystals are the most interesting, since they inhabit our 3-dimensional world, and they can be studied experimentally. From the point of view of a mathematician, 1-dimensional quasicrystals are much more interesting than 2-dimensional or 3-dimensional quasicrystals because they exist in far greater variety. The mathematical definition of a quasicrystal is as follows. A quasicrystal is a distribution of discrete point masses whose Fourier transform is a distribution of discrete point frequencies. Or to say it more briefly, a quasicrystal is a pure point distribution which has a pure point spectrum. This definition includes as a special case the ordinary crystals which are periodic. Excluding the ordinary crystals, quasicrystals in 3 dimensions come in very limited variety, all of them being associated with the icosahedral rotation group. The 2-dimensional quasicrystals are more numerous, roughly 1 distinct type associated with each regular polygon in a plane. The 2-dimensional quasicrystal with pentagonal symmetry is the famous Penrose tiling of the plane. And finally, the 1-dimensional quasicrystals have a far richer structure since they are not tied to any rotational symmetries. So far as I know, no complete enumeration of 1-dimensional quasicrystals exists. It is known that a unique quasicrystal exists corresponding to every Piso-Vieragavan number, or PV number. A PV number is a real algebraic integer, a root of a polynomial equation with integer coefficients, such that all the other roots have absolute value less than 1. The set of all PV numbers is infinite and has a remarkable topological structure. The set of all 1-dimensional quasicrystals has a structure at least as rich as the set of all PV numbers, and probably much richer. We do not know for sure, but it's likely that a huge universe of 1-dimensional quasicrystals not associated with PV numbers is waiting to be discovered. So here comes the connection of the 1-dimensional quasicrystals with the Riemann hypothesis. If the Riemann hypothesis is true, then the zeros of the zeta function are a 1-dimensional quasicrystal according to the definition. They constitute a distribution of point masses on a straight line, and their Fourier transform is likewise a distribution of point masses, one at each of the logarithms of ordinary prime numbers and prime power numbers. My friend Andrew Oslisko has published a beautiful computer calculation of the Fourier transform of the zeta function zeros. The calculation shows precisely the expected structure of the Fourier transform with a sharp discontinuity at every logarithm of a prime or prime power number and nowhere else. So my suggestion is the following. Let us pretend that we do not know that the Riemann hypothesis is true. Let us tackle the problem from the other end. Let us try to obtain a complete enumeration and classification of one-dimensional quasicrystals. That's to say, we enumerate and classify all point distributions which have a discrete point spectrum. Collecting and classifying new species of objects is a quintessentially Galilean activity, an activity suitable for frogs. We shall then find the well-known quasicrystals associated with PV numbers and also a whole universe of other quasicrystals, known and unknown. Among those multitude of other quasicrystals, we search for one corresponding to the Riemann zeta function and one corresponding to each of the other zeta functions that resemble the Riemann zeta function. Suppose we find one of the quasicrystals in our enumeration with properties that identify it with the zeros of the Riemann zeta function. Then we've proved the Riemann hypothesis, and we can wait for the telephone call announcing the award of the Fields Medal. Those are, of course, idle dreams. The problem of classifying one-dimensional quasicrystals is horribly difficult, probably at least as difficult as the problems which Andrew Wiles took 7 years to explore. But if we take a Galilean point of view, the history of mathematics is a history of horribly difficult problems being solved by young people who are too ignorant to know that they were impossible. The classification of quasicrystals is a worthy goal and might even turn out to be achievable. Problems of that degree of difficulty will not be solved by old men like me. So I leave this problem as an exercise for the young frogs in the audience. So section 3, Yuri Manin. Yuri Manin is a Russian mathematician for whom I have a deep respect. He recently published a delightful book of essays with the title Mathematics as Metaphor. The book describes for non-experts the spirit and flavor of modern mathematics while avoiding technical details. Manin is a prototypical bird, and mathematics as metaphor is a good slogan for birds. It means that the deepest concepts in mathematics are those which link one world of ideas with another. In the 17th century, Descartes linked the disparate worlds of algebra and geometry with his concept of coordinates. Newton linked the worlds of geometry and dynamics with his concept of fluxions, nowadays called calculus. In the 19th century, Boole linked the worlds of logic and algebra with his concept of symbolic logic, and Riemann linked the worlds of geometry and analysis with his concept of Riemann surfaces. Coordinates, fluxions, symbolic logic, and Riemann surfaces are all metaphors, extending the meanings of words from familiar to unfamiliar concepts. Manin sees the future of mathematics as an exploring of metaphors that are already visible but not yet understood. The deepest such metaphor is the similarity in structure of ideas between number theory and physics. In both fields, he sees tantalizing glimpses of parallel concepts, symmetries linking the continuous with the discrete. He looks forward to a unification which he calls the quantization of mathematics. Manin disagrees with the Galilean story that Hilbert set the agenda for the mathematics of the 20th century when he presented his famous list of 23 unsolved problems. According to Manin, Hilbert's problems were a distraction from the central themes of mathematics. Manin sees the important advances in mathematics coming from programs, not from problems. Problems are usually solved by applying old ideas in new ways. Programs of research are the nurseries where new ideas are born. He sees the Bourbaki program, rewriting the whole of mathematics in a more abstract language, as the source of many of the new ideas of the 20th century. He sees the Langlands program, unifying number theory with geometry, as a promising source of new ideas for the 21st century. People who solve famous unsolved problems may win the big prizes, but people who start new programs are the real pioneers. One of the richest sources of ideas for the 20th century was the program of research started by Georg Cantor in the 19th, exploring the world of infinite sets and infinite cardinals and ordinals. Hilbert picked out of this program a particular problem, the proof or disproof of the continuum hypothesis, which became number 1 on his list of 23. The problem turned out to have an answer that was deeper and more significant than Hilbert had imagined. Kurt Gödel in 1938 showed that the hypothesis could never be disproved, and Paul Cohen in 1963 showed that it could never be proved. The continuum hypothesis became a famous example of an undecidable mathematical statement, demonstrating that no single set of axioms can encompass the whole of mathematics. Manin is saying that the continuum hypothesis itself turned out to be unimportant. Few mathematicians today care whether the continuum hypothesis is true or false. The important progress was the understanding that many alternative sets of axioms may serve as foundations of mathematics. This understanding grew out of Cantor's program as a whole, not out of the particular problem of the continuum hypothesis. Manin discusses Cantor's program in a chapter of his book with the title Georg Cantor and His Heritage. He brings together two historically separate domains of mathematics, the theory of infinite numbers created by Cantor in the 19th century and the theory of finite computability created by Alan Turing in the 20th. Manin brings these two worlds together with a single statement. The statement is 2 to the power x is considerably larger than x. He remarks that deep mathematics begins as soon as we try to give a precise meaning to that word considerably. When x is infinite, and when considerably is interpreted to mean the smallest infinity, the statement becomes Cantor's continuum hypothesis. Statement says then 2 to the power x is the smallest infinity larger than x, when x is the set of integers, the set of whole numbers. So it says the set of points on a line is the smallest infinite set larger than the set of whole numbers. That's the foundation of Cantor's theory of infinity. When x is large but finite, 2 to the x is then roughly the number of operations required for a digital computer to answer a question about a number with x binary digits. The statement that 2 to the x is considerably larger than x means that most questions involving large numbers cannot be answered by a digital computer in a reasonable time. This statement is the basis of the modern theory of computability. The problem of deciding which arithmetical functions are in principle computable has no general answer. Manin suggests that this is no accident. There is a formal similarity between the Cantor theory of infinite sets and the Turing theory of computability of arithmetic functions. In both theories, undecidability is the rule rather than the exception, and the proofs of undecidability are formally similar. Each of those two theories is a metaphor for the other. So section 4, John von Neumann. Another important figure in 20th century mathematics was John von Neumann. Von Neumann was a frog, applying his prodigious technical skill to solve problems in many branches of mathematics and physics. He began with the foundations of mathematics. He found the first satisfactory set of axioms for set theory, avoiding the logical paradoxes that Cantor had encountered in his attempts to deal with infinite sets and infinite numbers. Von Neumann's axioms were used by his bird friend Kurt Gödel a few years later to prove the existence of undecidable propositions in mathematics. Gödel's theorems gave birds a new vision of mathematics. After Gödel, mathematics was no longer a single structure tied together with a unique concept of truth, but an archipelago of structures with diverse sets of axioms and diverse notions of truth. Gödel proved that mathematics is inexhaustible. No matter which set of axioms is chosen as the foundation, birds can always find questions which those axioms cannot answer. Von Neumann went on from the foundations of mathematics to the foundations of quantum mechanics. To give quantum mechanics a firm mathematical foundation, he created a magnificent theory of rings of operators. Every observable quantity is represented by a linear operator, and the peculiarities of quantum behavior are faithfully represented by the algebra of the operators. Just as Newton invented calculus to describe classical dynamics, von Neumann invented rings of operators to describe quantum dynamics. Von Neumann made fundamental contributions to several other fields, especially to game theory and to the design of digital computers. For the last 10 years of his life, he was deeply involved with computers. He was so strongly interested in computers that he decided not only to study their design, but to build one with real hardware and software and use it for doing science. I have vivid memories of the early days of von Neumann's computer project at the Institute for Advanced Study in Princeton. At that time, he had two main scientific interests, hydrogen bombs and meteorology. He used his computer during the night for doing hydrogen bomb calculations and during the day for meteorology. Most of the people hanging around the computer in daytime were meteorologists. Their leader was Jules Charny. Charny was a real meteorologist, properly humble in dealing with the inscrutable mysteries of the weather, and skeptical of the ability of the computer to solve the mysteries. John von Neumann was less humble and less skeptical. I heard von Neumann give a lecture about the aims of his project. He spoke, as he always did, with great confidence. He said, "The computer will enable us to divide the atmosphere at any moment into stable regions and unstable regions. Stable regions we can predict, unstable regions we can control." Von Neumann believed that any unstable region in the atmosphere could be pushed by an applied small perturbation so that it would move in any desired direction. The small perturbation could be applied by a fleet of airplanes carrying smoke generators, which would absorb sunlight and raise or lower the temperature at places where the perturbation would be most effective. In particular, we could stop an incipient hurricane by identifying the position of an instability early enough and then cooling that particular patch of air before it started to rise and form a vortex. Von Neumann, speaking in 1950, said it would take only 10 years to build computers powerful enough to diagnose accurately the stable and unstable regions of the atmosphere. And then once we had accurate diagnosis, it would take only a short time for us to have control. He expected that practical control of the weather would be a routine matter within the decade of the 1960s. Von Neumann, of course, was wrong. He was wrong because he did not know about chaos. We now know that when the motion of the atmosphere is locally unstable, it is very often chaotic. The word chaotic means that motions that start close together diverge exponentially from each other as time goes on. When the motion is chaotic, it is unpredictable, and a small perturbation does not move it into a stable motion which can be predicted. A small perturbation will usually move it into another chaotic motion which is equally unpredictable. So von Neumann's strategy for controlling the weather fails. He was, after all, a great mathematician, but a mediocre meteorologist. Edward Lorenz discovered in 1963 that the solutions of the equations of meteorology are often chaotic. That was 6 years after von Neumann died. Lorenz, who is still alive, is a meteorologist and is generally regarded as the discoverer of chaos. He discovered the phenomena of chaos in the context of meteorology and gave them their modern names. But in fact, I had heard the mathematician Mary Cartwright, who died recently at the age of 97, describe the same phenomena in a lecture in Cambridge in 1943, 20 years before Lorenz discovered them. She called the phenomena by different names, but they were the same phenomena. She discovered them in the solutions of the van der Pol equation, which described the oscillations of a nonlinear amplifier, published in 1945 with Littlewood. The van der Pol equation was important in World War II because nonlinear amplifiers fed power to the transmitters in early radar systems. The transmitters behaved erratically, and the British Air Force blamed the manufacturers for making the defective amplifiers. Mary Cartwright was asked to look into the problem, and she showed that the manufacturers were not to blame. She showed that the van der Pol equation itself was to blame. The solutions of the van der Pol equation have precisely the chaotic behavior that the Air Force was complaining about. I heard all about chaos from Mary Cartwright 7 years before I heard von Neumann talk about the control of the weather, but I was not clever enough to make the connection. It never entered my head that the erratic behavior of the van der Pol equation might have something to do with meteorology. If I had been a bird rather than a frog, I would probably have seen the connection, and I might have saved von Neumann a lot of trouble. If he had known about chaos in 1950, he would probably have thought about it deeply, and he would have had something important to say about it in 1954. Von Neumann got into trouble at the end of his life because he was really a frog, but everyone expected him to fly like a bird. In 1954, there was an International Congress of Mathematicians in Amsterdam. These congresses happen only once in 4 years, and it is a great honor to be invited to speak at the opening session. The organizers of the Amsterdam Congress invited von Neumann to give the keynote speech, expecting him to repeat the act that Hilbert had performed in Paris in 1900. Just as Hilbert had provided a list of unsolved problems to guide the development of mathematics for the first half of the 20th century, von Neumann was invited to do the same for the second half of the century. The title of von Neumann's talk was announced in the program of the Congress. It was Unsolved Problems in Mathematics, address by invitation of the organizing committee. After the Congress was over, the complete proceedings were published with the texts of all the lectures except this one. In the proceedings, there's a blank page with von Neumann's name and the title of his talk. Underneath it says, "No manuscript of this lecture was available." What happened? I happen to know what happened because I was there in the audience, at 3 o'clock in the afternoon on September 2nd, 1954, in the Concertgebouw concert hall. The hall was packed with mathematicians, all expecting to hear a brilliant lecture worthy of such a historic occasion. The lecture was a huge disappointment. Von Neumann had probably agreed several years earlier to give a lecture about unsolved problems and had then forgotten all about it. Being busy with many other things, he neglected to prepare his lecture. And then at the last moment, when he remembered he had to travel to Amsterdam and say something about the future of mathematics, he pulled out an old lecture from the 1930s and dusted it off. The lecture was about rings of operators, a subject that was new and fashionable in the 1930s. Nothing about unsolved problems, nothing about the future, nothing about computers, the subject that we knew was dearest to von Neumann's heart. He might at least have had something new and interesting to say about computers. The audience in the concert hall became restless. Somebody said in a voice loud enough to be heard all over the hall, "Aufgewärmte Suppe," which is German for warmed-up soup. Von Neumann, deeply embarrassed, brought his lecture to a quick end and left the hall without waiting for questions. So that's the end of chapter 4. Now, chapter 5, weak chaos. The phenomenon, if von Neumann had known about the phenomenon of chaos when he spoke in Amsterdam, one of the unsolved problems he might have talked about was weak chaos. The problem of weak chaos is still unsolved 50 years later. The problem is to understand why chaotic motions so often remain bounded and do not cause any violent instability. A good example of weak chaos is the orbital motions of the planets and satellites in the solar system. It was discovered only recently that these motions are chaotic. This was a surprising discovery, upsetting the traditional picture of the solar system as the prime example of orderly, stable motion. The mathematician Laplace, 200 years ago, thought he had proved that the solar system is stable. It now turns out that Laplace was wrong. Accurate numerical integrations of the orbits show clearly that neighboring orbits diverge exponentially. It seems that chaos is almost universal in the world of classical dynamics. Chaotic behavior was never suspected in the solar system before accurate long-term integrations were done because the chaos is weak. Weak chaos means that neighboring trajectories diverge exponentially but never diverge far. The divergence begins with exponential growth but afterwards remains bounded. Because the chaos of the planetary motions is weak, the solar system can survive for 4 billion years. Although the motions are chaotic, the planets never wander far from their customary places, and the system as a whole does not fly apart. So, in spite of the prevalence of chaos, the Laplacian view of the solar system as a perfect piece of clockwork is not far from the truth. We see the same phenomena of weak chaos in the domain of meteorology. Although the weather in New Jersey is painfully chaotic, the chaos has firm limits. Summers and winters are unpredictably mild or severe, but we can reliably predict that the temperature will never rise to 45 degrees Celsius or fall to -30, extremes that are often exceeded in India or in Minnesota. There is no conservation law of physics that forbids temperatures from rising as high in New Jersey as in India, or from falling as low in New Jersey as in Minnesota. The weakness of chaos has been essential to the long-term survival of life on this planet. Weak chaos gives us a challenging variety of weather while protecting us from fluctuations so severe as to endanger our existence. Chaos remains mercifully weak for reasons that we don't understand. That is another unsolved problem for young frogs in the audience to take home. I challenge you to understand the reasons why the chaos observed in a great diversity of dynamical systems is generally weak. So finally, Manin again. To end this talk, I come back to Yuri Manin and his book, Mathematics as Metaphor. The book is mainly about mathematics, but it may come as a surprise to Western readers that he writes with equal eloquence about other subjects such as the collective unconscious, the origin of human language, the psychology of autism, and the role of the trickster in the mythology of many countries. To his compatriots in Russia, such many-sided interests and expertise would come as no surprise. Russian intellectuals maintained the proud tradition of the old Russian intelligentsia, with scientists and poets and artists and musicians belonging to a single community. They are still today, as we see them in the plays of Chekhov, a group of idealists bound together by their alienation from a superstitious society and a capricious government. In Russia, mathematicians and composers and film producers talk to one another, walk together in the snow on winter nights, sit together over a bottle of wine, and share each other's thoughts. Manin is a bird whose vision extends far beyond the territory of mathematics into the wider landscape of human culture. One of his hobbies is the theory of archetypes invented by the Swiss psychologist Carl Jung. An archetype, according to Jung, is a mental image rooted in a collective unconscious which we all share. The intense emotions that archetypes carry with them are relics of lost memories of collective joy and suffering. Manin is saying that we do not need to accept Jung's theory as true in order to find it illuminating. More than 30 years ago, the singer Monique Morelli made a recording of songs with words by Pierre Macolin. One of the songs is La Vie Morte, the Dead City, with a haunting melody tuned to Morelli's deep contralto, with an accordion singing counterpoint to the voice, and with verbal images of extraordinary intensity. Printed on the page, the words are nothing special. I won't try to read this in French because my French is too bad, so I give you just the English translation. As we entered the dead city, I held Margot by the hand. We walked from the graveyard on our bruised feet, without a word, passing by these doors without locks, these vaguely glimpsed holes, these doors without a word, these garbage cans full of screams. I can never listen to that song without a disproportionate intensity of feeling. I often ask myself why those simple words of the song seem to resonate with some deep level of unconscious memory, as if the souls of the departed are speaking through Morelli's music. And now, unexpectedly, in Manin's book, I find an answer to my question. In his chapter, The Empty City Archetype, Manin describes how that archetype of the dead city appears again and again in the creations of architecture, literature, art, and film, from ancient to modern times, ever since human beings began to congregate in cities, ever since other human beings began to congregate in armies to ravage and destroy them. The character who speaks to us in Macolin's song is an old soldier who has long ago been part of an army of occupation. After he walked with his wife through the dust and ashes of the dead city, he hears once more the magic calls of a bugle. This is the end of the song. The magic calls of a bugle that came to life for an hour in an old soldier's dream. The words of Macolin and the voice of Morelli seem to be bringing to life a dream from our collective unconscious, a dream of an old soldier wandering through a dead city. The concept of the collective unconscious may be as mythical as the concept of the dead city. Manin's chapter describes the subtle light that these two possibly mythical concepts throw upon each other. He describes the collective unconscious as an irrational force that powerfully pulls us toward death and destruction. The archetype of the dead city is a distillation of the agonies of hundreds of real cities that have been destroyed since cities and marauding armies were invented. Our only way of escape from the insanity of the collective unconscious is a collective consciousness of sanity based upon hope and reason. The great task that faces our contemporary civilization is to create such a collective consciousness. Thank you.